Well, hello. We're coming to you live on a cold and rainy day to speak with you about reliability. This is one of a series of presentations on test theory and its applications. So here we go. Reliability is one of the big central ideas in classical test theory. And you may recall, if you were present for an earlier presentation, is that the initial insight underlying classical test theory, also known as psychometric theory, is that every time we take a measurement, what we get, the result, is a mixture, a blend of truth with error. We know that it's also possible to describe, to quantify the random or sometimes called statistical errors that occur in the course of taking repeated measurements. And once we know the result we've obtained and the error, we can estimate how much truth is in the assessment that we're conducting. That's what's known as reliability. So there are various definitions one will find of reliability in textbooks and presentations. Probably the most common near synonym presented is the word consistency. Does the test, does the measurement instrument give you consistent results, meaning from time to time, how similar are the results you're going to get? Another term, which is probably a little better, would be precision. We see this more in engineering contexts than we do in psychology or education, but it really is another way of saying the same thing. To the extent that a measure is precise, there is little random error built into it. That's the same thing as to say reliability. If you want a really precise definition of reliability, though, it's quite simply what proportion of whatever I'm getting is true. So remember, it's always a mixture of truth and error. So if you take the truth and divide by the truth plus the error, you're going to get theoretically, some number between 0, utterly random test you should throw away immediately, and 1, impossibly perfect test that no one will ever believe. So that's the gist of it. Now, the conceptual equation that the result is equals to truth plus error is purely conceptual, but there are ways of calculating what we call reliability coefficients we'll get to in just a moment. Of course, we want our measures to be as reliable, as precise, as consistent as possible. If you stick around for several more of these presentations, you will hear me say this probably on several occasions. There are really only 2 ways of doing that. You want a better test? One option, make it longer. Whatever your measurement is, each time you try it, you're getting what you might call a fallible indicator of whatever it is that the test is tapping into. So if you keep doing it over and over, those random errors, the little odds and ends, start to cancel one another out. So the 5-item quiz becomes a 20-item quiz. The 3-judge panel becomes a 5-judge panel, et cetera, et cetera. The only other thing you can possibly do is to actually improve the individual measures that you're taking. Write better items on your exams if you can. Write better items for your personality test, or develop more evocative ink blots, or develop a rating system that your judges can use that they will that will enable them to stay closer and closer to coming up with the same results. We'll come back to that probably in other presentations, as I say, because that's really at the heart of test development and improvement. But now, if you really want to wrap your head around reliability and not just use synonyms and sort of fake equations, just conduct this little thought experiment. Imagine a person taking a test. There they are, taking their test. Now, imagine that we grant you mystical, magical powers extraordinaire, and you can refract that person into thousands, tens of thousands of parallel universes all across the Morkockian multiverse. There is the same person taking the same test under the same conditions? Well, if you did that, how similar will the results be? That's it. That's reliability. Now, of course, the problem here is that we don't have those mystical, magical powers, and we can't do that. So what we have to come up with are ways of estimating what would happen if we could. And that's where the different types of reliability are going to come into play. When you do one of these procedures to come up with a reliability estimate, the estimate is expressed as a number. It's known as a reliability coefficient, typically represented by a lowercase italicized r with this, either the subscript 11 or the subscript xx, depending on whose textbook you're reading. R, if you've taken any kind of statistics class, and if you haven't, I'm not quite sure why you would be here. R is the correlation coefficient, the Pearson product moment correlation coefficient, or one of its variants. And so usually, if you're going to be real technical about it, you would write R sub 1, 2 or R sub XY, meaning that you're getting the correlation between measure 1 and measure 2, or measure X and measure Y. When you put 1, 1 or XX, what you're basically saying is, how strongly does this test correlate with itself? Which is an odd way of putting it. You'd think it would correlate perfectly with itself because it's the same thing, but it's not, because there's that error, that random error built in, and randomness doesn't correlate with anything. So you will get a number between 0, right? Totally random test, throw it away immediately, and 1, impossibly perfect test. We're going to probably accuse you of scientific misconduct. You're going to get a number in that range, just as you do when you run a correlation coefficient. And in fact, most of the ways we get reliability coefficients are essentially correlational procedures. That's really all there is going on here. Another way of thinking of this, by the way, is that you're looking at something like a signal to noise ratio. You turn on a radio in your car that actually has an antenna, and you're getting a broadcast signal. You hear the song or the talk show you're listening to, but you also hear static. And so everything you're getting is a mixture of the true signal with the random noise. And what you want, of course, as you're trying to tune your radio in while swerving through traffic, is to get as much signal and as little noise as possible. Once we have a reliability coefficient, and again, this will be a number like 0.82 or something like that, we can use that and our knowledge of the other properties of the test, mainly the standard deviation of test scores, to derive something called a standard error of measurement, variously represented as S subscript EM or S subscript ERR, for obvious reasons. What you have to remember here is that random errors are distributed normally around the central value. We hope, of course, the central value is the truth. We treat it as such. And so you're going to have this symmetrical arrangement with most of the errors being pretty small, some one way, some the other, and then some of them a little more extreme. And you all remember, I hope, that a standard deviation is a measure of variation that we use, especially when we have normally distributed variables. So the standard error of measurement is quite simply the standard deviation of the errors. The mean error is 0 by definition, but what's the standard deviation? And so this is a function of the reliability. You see, the higher the reliability coefficient, the lower the standard error is going to be. Now, the standard error is important because it gives you a sense of, how should I put this, how far off the results you obtained might well be. We hope, of course, that we're getting something close to the exact truth, but we have to recognize the limitations of our measurement procedures. So what we can do is to set a given level of confidence. Let's say I want to be 80% sure that the range of test scores I'm talking about includes what would be that person's true score. I can use the standard error of measurement to construct these so-called confidence intervals. And again, when you're administering a test, the score you get is only an estimate of what their true score would be. There is random error built in there. So the confidence interval tells you, to whatever degree of confidence you desire, what range is possible, where their true score might lie. That's what it's for. Now, notice we're not doing any calculating today. We have other presentations about deriving reliability coefficients using various procedures, deriving the standard error of measurement, constructing confidence intervals, and so forth. Not today. This is all conceptual today. Okay, so our old friend, the normal distribution, just to remind you if you haven't looked at one lately. So you'll notice, the midpoint is represented by the Greek letter mu there for the mean. And as you go out, count out by standard deviation units, you're capturing more and more and more of the cases. In this case, we're speaking of what would happen if you were to keep testing that person in every corner of the multiverse, poor soul. So how do we estimate reliability? We actually have 4 ways, of which probably the latter 2 are the most widely used, but for very different purposes. I do want to emphasize that each of these is only an approximation, and also that no one of them applies to every kind of test or measure. So there are going to be, in most cases, maybe 1 or 2 of these, maybe sometimes 3, that are relevant to the test you're developing. So they're test-retest reliability, parallel forms, which has multiple names, alternate forms, equivalent forms, etc., internal consistency, and inter-rater, also with multiple other names, inter-judge, inter-scorer, and so forth. We're going to look at each of these in turn, again, with no calculations today. Test-retest is always a good place to start because it's the most similar to that thought experiment, right? And in that sense, it's pretty intuitive. You're telling me the results on this test are pretty consistent. Well, what happens if I retest somebody, right? How similar will the scores be? That's really all it's about. So this is important, very important, to the extent that you're measuring something that's supposed to stay about the same. I'm an adult. My height is not expected to change dramatically, over the next 6 months or a year. So if you're measuring my height with some device or other, you would hope that you would get pretty consistent results from occasion to occasion. There are minor fluctuations in height. By the end of the day, we're a little shorter because, gravity, and we get a little longer as we stretch out and sleeping at night. And then there also is random error built into your use of your yardstick, your measuring tape, or whatever device you're employing. But it should stay pretty comparable. So if you had this, the sometimes termed the rubber ruler that keeps seeming to give you different results on different occasions, that's a bad measuring tool. Sometimes the reliability coefficient we're deriving here is called a stability coefficient because it is measuring how stable something is over time. Some psychological constructs are supposed to be pretty stable. IQ after about age 7 or 8 is supposed to be pretty stable, not unchanging, pretty stable. Major personality traits like extroversion or neuroticism, pretty stable. Now, that's not to say these things don't change at all over time. They do, sometimes dramatically, but on average, they tend to stay pretty close to where they were. My level of extroversion today relative to people of my age is probably pretty similar to what it was 20 years ago or 40 years ago relative to people of my age at the time. All right, so here's how you get it. And this, you couldn't get a lot simpler in principle. You get a bunch of people to take your test, and then some future date, you get the same bunch of people to take your test again. You score the test for both occasions. Now you have 2 data points per person. You simply calculate a correlation coefficient, good old Pearson correlation, and that's your reliability coefficient. You're done. The only thing that makes this at all complicated, of course, to do is getting the people to come back. So it's always tempting to try to knock this off fast, test them again right away, or bring them back tomorrow or something. What you do run into a conceptual problem here, which is that the longer you wait, the lower the correlation is going to be. So you don't really have one test-retest correlation for a test. You really have as many as you have checked out intervals. By the way, this makes sense, right? If you retest me right away, of course I'm going to say pretty much what I just said 5 minutes ago. If you retest me 2 weeks from now, probably going to be pretty similar, but I'm not going to have everything active in my memory of like, oh yes, I remember how I answered that. If you measure me 6 months later, I might even have changed a bit. And at least some people in your sample probably will have. So the longer the interval, the lower the correlation tends to be, which means you have to take that into consideration when you're interpreting the test-retest reliability coefficient. You see test-retest reliability of, say, 0.84. If that's in a 2-week interval, you're like, okay, the test holds up fairly well, but you're not super impressed. If it's 0.84 correlation after 6 months, you're like, all right, this thing is, this is stable. Okay. But that's test-retest. The second form is what's called parallel forms reliability. Again, this one has several names depending on whose textbook you're reading, and that's not my fault. But this is the most specialized one. This is the one you will encounter the least, and even if you go into the test development business, you may or may not ever have to deal with it. This one applies only if you're going to try and have at least 2 different versions of a test, which is to say, all the items on the test are different, but it's supposed to be the same test, which is to say, no matter which one I take, I should get pretty much the same score. Well, that's a pretty tall order. You try writing 2 50-item midterms with all different questions and ensuring that it doesn't matter which version the students take, they're going to get the same score. Why don't we do this more than we do? It's just a huge amount of work, right? Developing a test is a lot of work. So, wow, I have to now develop 2 forms. That's almost twice as much work as I needed to develop one. And why do I need 2 forms anyway? Well, that's why it is sometimes done. What if I need to test the same people repeatedly and I'm concerned about practice effects? So where do you see this? You see it on some achievement tests, like reading tests, for example, because you're going to have students who are diagnosed with reading problems and develop, an IEP will be developed for them and they'll be referred to the reading specialist and or the special education department. And you're working with them over the next 6 months or the full academic year. And then at the end of that span, the question is, well, how are they reading now? And you might be doing that from the 2nd grade when you first diagnosed the reading disorder all the way up, into 11th or 12th grade. If you keep giving them the same test every 6 months or even every year, you're going to run into the problem that they just kind of know that test. So it's nice to have 2 versions of it. And you'll also see this for the same reason with language tests, because people who are being referred, children who are being referred for speech therapy and to try to build their expressive vocabulary or what have you, will need to be retested to see if any progress has been made. So how do you get it? It's real easy, actually. The hard part here is, creating the test and then actually getting good enough results to say that you have 2 forms of it. You get the folks to come into the lab and they take both forms. If you're going to be proper about this, half of them will take Form A followed by Form B, and half will take Form B followed by Form A. So you're counterbalancing order of presentation, but that's it. There's nothing else to it. You score the 2 tests, correlate them, and you have a reliability coefficient. You're done. One and done. However, there are a couple of things to bear in mind here. We are saying it literally doesn't matter whether you take Form A or Form B, you're going to get basically the same score. that means that the reliability, this form of reliability coefficient ought to be real high, like well into the 90s, 0.93, 0.94, 0.95. It also means that the distribution of scores should be similar. At least the mean or average shouldn't be significantly different. Even if we had 0.9 correlations between two versions of a reading test, if the average kid taking one got a score of 95 and the average kid taking the other got a score of 105, those are not comparable. They're not equivalent, and so what if you gave the tougher one first and the easier one later? It's going to look like your year of reading tutoring has done amazing things when it's actually maybe not. But if you did it the other way around, you could have done good reading tutoring and it'll look like they're losing ground, right? So you need to meet a very high bar with this, which is where all the work comes in. Now we get to internal consistency. This is really the most widely reported form of reliability by far, because it applies to most every test we develop. Not every, but most. You have a 10-item quiz, you're adding the scores for 10 items. Each item's a measurement. You're saying that the 10 items are measuring the same thing. Prove it. That's your goal here. You have, 20-item personality scale measuring extroversion. Every item on the scale is supposed to measure extroversion. But you don't know that they are. You don't know that's happening. It's a hypothesis, and you're going to have to test it by calculating the internal consistency of the test. Notice internal, like inside the test itself, is where we're going here. Now, whatever it is that all the items have in common, that's captured by this internal consistency statistic. So whatever it is that's unique about this item or that item, whatever it is that's random about this item or that item, that's not helping you. All that you really want is whatever it is, they all share. That's it. So there are a few ways of getting at this one. Again, this is not going to be calculation day, but conceptually what you have to remember is that each item is a measurement. You score each item separately, and each item's score actually has 3 different things going on in it. What you're after is what it shares with the rest of the test, as I've been saying. There's also going to be something unique to that item, and there's going to be just some random error or noise. If I ask you on some kind of a quiz or knowledge test, where should you go to find giraffes living in the wild? And you answer Africa, and you're correct. To some extent, you know that because you know a lot of stuff, or you don't know it because you don't know very much. To some extent, you know it because you're interested in wild animals, or because you're interested in Africa, not because you know a lot about everything in general, but because you have this narrow area of focus that you've learned about. And some of it is just random. It's just, you happened to be flipping through the channels last night and you landed on some nature documentary, and they were like, and here we see in the African savanna, elegant giraffes, and you're like, and the next day you're like, oh, it's right here on the test. This is great. I just saw a giraffe yesterday. It was in Africa. That's kind of a random event, right? So it's really only the shared variance that matters. And again, all the ways we have of calculating this are just ways of getting at that. The 3 methods, again, not being calculated today, this is just so you know that they exist, are the split half approach, which is the oldest and simplest. You basically treat the test as if it were 2 tests, score this half, score that half, and correlate them. And then 2 more advanced approaches, the Cooter-Richardson Formula 20 and Cronbach's coefficient alpha. Those are superior for most purposes to the older split half approach. Again, you'll see all of these reported in papers. Cronbach's alpha probably more than any other. In fact, that one has become so common that you'll often just see the little alpha Simple, they'll say the test had excellent reliability, alpha equals 0.92. And, they're just assuming that if you're reading this paper, you know what that means. Are there other methods? Absolutely. There are always statisticians that work on these things, coming up with new and arguably improved methods, but these are the biggies that you see all over the place. And that gets us to the last form, inter-rater reliability, after which we can conclude for today. Inter-rater reliability is, in my judgment, very important, although it often isn't discussed as extensively in psychometric textbooks. This one comes into play to the degree that one must exercise judgment in scoring, rating, or evaluating a product. So it's utterly irrelevant on multiple choice tests or on self-report personality questionnaires where there's a simple answer key, but it's relevant on anything where you as the scorer have to pause and think, how much credit do I give that response? So think about things like term papers, essay exams, oral presentations, just to name a few obvious academic examples. Think about things like judgments of fitness for duty after a psychological evaluation of a first responder who's been traumatized. Think about an evaluation of a grant proposal for someone wanting to start a nonprofit community service organization, or a business plan by someone who's looking for a bank loan to get started or go into the Shark Tank. Think about a judgment being made of a gymnastics performance at the Olympics or a figure skating performance at the Winter Olympics. In all of these cases, someone has probably raised in a conversation the question, well, isn't that just subjective? Well, that's an empirical question. It's worth asking. We should, in fact, look at the inter-rater reliability of gymnastics and figure skating coaches, of bank loan officers and grant funding agencies, and college professors and high school teachers. Yeah, we should. The real question we're asking is not whether it's just subjective, though. It's how objective versus subjective are these measurements? And what that question really boils down to is, how closely do independent observers agree as to what it is that they're seeing, that they're in their judgments, in short? That's it. Mind you, independence is a crucial element in this. If two people sit down together to make a judgment and they're passing notes back and forth or whispering to one another, or even signaling with facial expressions what they're thinking, they are not independent judgments. It's an entirely different issue. Yeah, we can agree on something if we try. The question here is whether, if you're not communicating with each other, you nonetheless come up with similar results. So essentially, inter-rater reliability is the psychometrician's way of saying objectivity. And it's not all or nothing. As with any form of reliability, it's quantified. Now, in this case, the statistical approach we take differs depending on what kinds of ratings we're making. So sometimes we're making straight up categorical judgments. Is this or is this not a case of schizophrenia? Would be a very good clinical example, right? And in such cases, we're really on a nominal scale, and we're going to use one set of procedures. On other occasions, we are making dimensional ratings. We're scoring the grant proposal on a 1 to 100 scale. We're rating the gymnast on a 1 to 10 scale, and so forth. And here we're, at least in principle, on something like an interval or ratio scale. So we use different statistics. When it's a categorical judgment we're making, is it schizophrenia? We start by calculating percentage of agreement. How much of the time do the judges agree? Let's just keep it to 2 judges, just to keep life simple. So how much of the time are they agreeing? And then you have to make an adjustment, because you have to calculate how much they would be expected to agree if they were just guessing. if they really had no basis for making judgments, but they were essentially just tossing coins or throwing dice, how much of the time would they get the same result? And then you make this little adjustment, and there's the usual statistic here is something called Cohen's kappa or coefficient kappa, kappa coefficient. Again, there are others out there like Krippendorf's alpha, but Cohen's kappa is the one you see the most. Cohen's kappa represents how much more closely judges are agreeing than they would have agreed if they were just guessing. How much of an improvement are we making on chance? And you see this in studies of diagnostic reliability, for example, when they're developing a new edition of the DSM. The other type of judgment, of course, is a dimensional one. We're assigning some kind of score to you on some kind of scale, like a 1 to 10 scale. Here, there actually are two approaches. There's a variant on the Spearman-Brown prophecy formula, which works just fine. And there's something known as the intra-class correlation coefficient, which also works just fine. And, they're pretty similar, and they tend to give you real close to the same results, though the ICC sometimes it is a little bit more conservative. So sometimes you get noticeably lower results with the ICC approach. Most of the time, they're so close that it really wouldn't matter which one you did. Last topic for the day is the whole subject of test length and reliability. Remember that one of the ways of making a test more reliable is to make it longer, right? And add items to it. Now, the new items have to be about as good as the ones you had. You can't just write random garbage, but if you do make it longer, in general, it's going to get more reliable. And there are then questions that arise, like, okay, my test, as I've written it, isn't reliable enough. I'm only getting reliability coefficients of 0.64, and I want it to be much better than that. What I'd like to know is how many more items do I have to write? How much more work do I have here? And there are occasionally you have the opposite situation. I've got this great test, but I want to give it as part of a huge study, and I can't give the whole big long test, so I have to hack the thing down, make it shorter. But will it still be reliable enough to use when I discard 2/3 of the items? Yeah, delete items. Well, there are formulas for this, right? You can calculate the likely effect of making a test longer or shorter and have some idea of what you need to do moving forward. Okay, we're again not doing calculations today. That's another presentation. So today we have really delved into what reliability is. We've explored the major forms of reliability. And again, in other separate presentations, we're going to look at how to calculate and derive reliability coefficients, internal consistency, inter-rater reliability in particular, how to get a standard error of measurement, and how to construct confidence intervals. In terms of our conceptual approach, the next big idea, the second of the big ideas in classical test theory, will be validity. And that said, we are done for today. Thank you all very much.